thank you everyone for joining this Moldex 3D webinar. This is actually part 2 of our lightweighting series where I'll be going over the gas-assisted injection molding process. So just a reminder, as we get started, make sure that you keep your microphones muted. We want to make sure that the recording stays nice and clear for those listening to the webinar afterwards. And speaking of which, after this webinar is completed, you'll be receiving a survey. If you fill out that survey, then you'll be able to receive a recording of this webinar, which you can share with your colleagues or reference at a later date. All right, so just as a quick introduction to what we're going to be going over, so the gas-assisted injection molding process, what goes into it, how it differs from some of the other lightweighting processes out there. All right, gas-assisted injection molding features and benefits, how this process can help you in your injection molding process, as well as how Moldex 3D can help us to simulate this process before bringing it in shop. All right, some results that we typically go over, some case studies, and then a final conclusion to wrap things up. All right, so starting off here, just kind of looking at a little bit of what goes into the gas-assisted injection molding process. And if you joined the webinar for the first part of this lightweighting series, you would have seen the microcellular injection molding or foaming side of the lightweighting processes. And the gas-assisted injection molding process is actually very similar to that, except instead of a distributed bubbles, we're going to be kind of applying a bulk gas. And that bulk gas is going to replace a vast majority of the material in our part, which is where the lightweighting comes from. And also similar to some of the foaming processes out there, this injection of gas is actually going to help us to push the material out to the end of fill, which is going to remove a lot of the need for any sort of packing. So that the air here is actually going to help us to pack out the part, rather than applying a constant pressure from our injection point here. So beyond that, because this gas is helping us to distribute the pressure a little bit more evenly across the majority of our part, we're able to eliminate a lot of the sink marks, we're able to increase our dimensional stability, and we're able to obviously make the part a little bit lighter because of that replacement of material due to the gas. All right, so a couple of parts here. You can see some of these traditional parts are actually able to be created by the gas-assisted injection molding process. And I mentioned a lot of the advantages before, so you get a decreased cycle time, you get a more reliable part, you get a lighter part. There's a lot of benefits to this sort of process. One of the main disadvantages of using the gas-assisted injection molding process over something like a MeluGas or some other foaming process is that the actual behavior of the gas, how that gas actually distributes to your part, is quite unpredictable. And once you nail down the process and once you are able to replicate a process reliably, then the gas penetration is usually pretty consistent. But being able to predict before actually injecting the part and before injecting the gas, where that big gas bubble is going to appear inside your part, which is this blue region here, that's actually very difficult to predict, especially for long, thin parts with a high flow length ratio. It can be very difficult to actually predict what's going to happen with the gas, and that's where simulation can help us quite a bit. Is being able to predict what's happening. What's going to happen in the part based on the amount of pressure we apply to the gas, based on the amount of material that we inject before we inject the gas, based on the amount of time that we're injecting both of these materials or both of these media. We can figure out pretty generally and pretty reliably what kind of process we're going to need for this sort of part. Another thing you can actually model in Moldex 3D is what's called an overflow. An overflow is very common in the gas-assisted injection molding process, just because we're injecting a small amount of material, and then we're allowing this gas bubble to push the material out towards the end of fill. So we'll see this in a little bit later of a slide in a little bit more detail. But this process is very easy to control once we're able to nail down the process and figure out where this gas bubble is going to be located. All right. So process validation. So there's three main control factors that we look at when it comes to gas-assisted injection molding. So we have the assisted gas time. So how much time it's going to take to, or how much time we're actually going to be injecting air or gas, how much time between when the melt starts and when the gas starts, we call it the delay time, the gas location, and optional is an overflow region and dimensions of that overflow region. The overflow region is really just used as a kind of like a buffer. So when you're first figuring out your process, you don't actually know how much material to inject versus how much air to inject. So if you inject too much material, then that material will just push into the overflow and you can just cut that off after the part's been molded. Whereas if you didn't have the overflow, then you would just be packing out your part using the air a little bit more than you may desire. So that's where the overflow can help us a little bit. All right. So the conditions optimization. So like I mentioned, being able to model in this overflow is going to be very advantageous, but there's actually another type of method that you can use as well. It's more of like a trial and error. It's called the short shot method, where you'll basically shoot a bunch of short shots, and then based on the amount of air that's being introduced into the part, you can calculate how much time difference you're going to need between the two injections. So that's what's known as the short shot method, and like I mentioned before, the overflow method is kind of the opposite way. So you'll have an overflow, you'll shoot into the overflow, and then you'll reduce gradually the amount of material that you're injecting until you get just the part shot, and in which case you wouldn't need the overflow. You can always keep the overflow in your design, but once you optimize this process, you probably shouldn't need the overflow any longer. All right, so two of the results here that we typically look at just for the gas penetration behavior. First of all, the melt front time. You can see that the melt front kind of hesitates once we inject all of our material. And then past that, we're basically just relying on the air to push out our melt front to the end of fill, or past the end of fill into the overflow region if we have it. The other one is our gas front time. So evaluating how much time we're actually taking to inject this gas. If the gas only gets a certain amount through our part, and then our part starts to freeze, then any time after that freeze point, we don't really need to apply any more pressure to the gas because the gas isn't going to penetrate any further. So this is something we can use to just kind of optimize our process and reduce our cycle time a little bit if need be. All right, and then the last one that we typically look at, one of the most important ones here, is the thickness distribution on the skin. So when we're injecting this air through our part, actually our part thickness is going to be reduced in that region where the air is injected. So like I mentioned before, that's one of the strengths of running the gas-assisted injection molding simulation, is being able to predict the behavior of where this gas is actually going to end up. Similarly, we can predict how thick that core is going to be, how much of the air is going to take up the thickness of our part. and as a result, we'll be able to determine what the final part thickness is in that region. That can be very important from a structural standpoint. All right, so looking into a couple of case studies here. So the first one is just a flow length study. So we have just a regular melt inlet here. It's going to inject material, and then once we get to this point, the gas is going to turn on and push the melt, ideally, all the way to the end of fill through this plaque. So you can see that with the simulation, you can actually see that the gas is penetrating in this dark, or this gray color is the gas, and then obviously the non-gray color is the part. So really what they were trying to envision with this study was, you can almost consider the plaque as almost like an overflow. Really, we're just looking at this semi-cylinder or half cylinder and looking at how far the gas actually flows. You can see that the behavior of the gas flowing through this channel is very, very similar to what the simulation predicts. All right. And you can see this on many different parts. We actually have a lot of, few different case studies here. And you can see the gas penetration behavior. This is actually just a scan of the part, being able to tell us where that gas is going to end up. And in Moldex 3D as well. All right, looking at the cut of this part, so cutting open this part and seeing what the actual gas penetration behavior looked like in reality versus what happened in Moldex 3D, you can actually see that the behavior is very similar. And really being able to predict what regions of the part are actually going to be penetrated into is the most important thing. So for something like a steering wheel, if I'm going all the way out to my end of fill, then I might be having some problems with packing out my part completely. If I don't get all the way out to my end of fill, I might also have different problems with packing out my part completely, maybe even difficulty filling out my part completely. So being able to predict where this material is, or where this air or gas is going to end up in our part, is the most critical aspect of the gas-assisted injection molding process. You also have one more problem that I don't really have laid out in this presentation, unfortunately, but there is one more problem, and that's called blowout. So if the gas actually gets all the way to the end of fill and is not able to push the material further, but rather just cuts through the material and blows out the end of fill, then you're not actually pushing the material using the air. You're just blowing air through your part at that point, and you'll usually get a short shot. So that's another thing that the simulation can actually predict. If the material is no longer able to push forward, but the gas is able to push through the material, you will see that sort of blowout condition occasionally. All right, so another case study here, just a simple test plaque, or I guess kind of like a spiral mold type scenario. We actually have two penetration points. We have the primary penetration, which is kind of right here in the middle. And then we have a secondary penetration point, which is closer to the end of fill. And these are basically just measure points. This is where we're actually measuring where the material is, or where that gas is starting to slow down in penetration. So you can see that once we get all the way out to the primary penetration here, you can see the thickness of this core is actually reducing, and it'll gradually reduce until the end, where right about here, which is also where the simulation predicts that it will also start to end. You can actually see that the primary penetration and the secondary penetration regions are actually very similar as far as the hollow ratio distribution, which is basically just the ratio of the inner diameter versus the ratio of the outer diameter, based on how much of the gas penetrated into the part. All right, so a few real case studies. So those were really just kind of test plaques and some test parts. So looking at some real case studies here, the first one is this Lydion part. All right, so you can see the flow distribution, nothing too groundbreaking. The flow distribution is really just like a normal injection molding until we start to inject that gas. You can see that the sink mark is greatly improved, which was one of the big points on this part. It's actually a relatively thick part with respect to its length. So they were having a lot of sink mark problems, especially with some of these ribs on the top side. So one of the main advantages of GAIM is being able to kind of hollow out those regions and provide a more even distribution of packing through the part, which means that the likelihood of having a sink mark is much lower. And then also with this part, warpage, it was kind of a structural part, so we want to make sure that the warpage is as reliable as possible. And we can see that just looking at the scales, the X displacement was reduced by about 45%, Y displacement was reduced by about 40%, and the Z displacement was reduced by about 64%. And you can actually see that with the Z displacement result, the trend actually reverses. So you can see that it's a little bit higher in the middle and much lower towards the outside, where it's the opposite with conventional injection molding. So that's something that you might also see, and that's just a result of the air packing out our part a little bit more reliably. Whereas with conventional injection molding, when we have 2 injection points, like on this part, those injection points are what we're depending on to actually pack out the material in our part. When we're actually injecting the air, we're allowing that air to assist us with packing out the rest of our parts. So that can actually reverse the warpage trend a little bit in some cases. And then you can also see here the gas penetration behavior is quite reliable. There are some ribs that the air is blowing into, and those can be kind of unpredictable sometimes how far they're going to be penetrated into those ribs. And from simulation, it can be a little bit difficult to predict that length, but you can see that the simulation predicts that there is some sort of penetration into those regions. And you can see the similarities between some of these gas penetration regions from simulation versus reality. All right, so the Lydion case, we were able to reduce the sink mark displacement, and we were also able to reduce the amount of total warpage on this part as well, which is a huge benefit to them. All right, the second one here on a rear view mirror connector piece. So this is actually what you would see in your car. This is the little tab here. So this ball socket is actually going to connect into this circular region, and it's very important that this circular feature is as circular as possible. We don't want it to bend unevenly in one direction. We don't want it to become an oval like in this picture here. We want to make sure that the circularity is maintained as best as possible so that ball socket is able to fit very reliably. So a couple of the problems that they had with this part, first of all, they were seeing a lot of sink. And actually, this isn't really sink. This is more of a void type condition. So the material is actually internally shrinking, and that's causing a very large internal void in our part, which is what you see here. And that's because of the high temperature out in this region. So one of the things that GAIM can help us to do, if we can just push air out into those regions, we can reduce the thickness of the part in that region, which will reduce the likelihood of temperature being kept in that local hotspot. So being able to push material into these regions is going to help us to reduce this likelihood of a void or even a sink mark or anything like that. All right. So process parameter modification. So the first thing that they tried was to increase the amount of packing time. So they started with 15 seconds, which gave them a packing melting core distribution, melting core just being the amount of material above the freeze temperature. So this is a resultant Moldex 3D that you can show, and this is very similar to the trend that they would see in reality if they were to cut it open and take a temperature gun to it. So this is something that we can show very easily, and as they increase the amount of packing time, you can see that this molten core gradually reduces, but it's not until like 35 to 40 seconds into packing when this material is actually cooled down sufficiently to remove the possibility of having any sort of void in there. So we have to constantly apply pressure for 35 to 40 seconds in order to get a nice part out of here, and that is just absolutely unacceptable. So they needed to look to other sorts of processes in order to figure out what to do with this part. All right, so the main area of concern again is over in here, and also around this ring, they were seeing a shrinkage variation. Actually, I kind of skipped over it before, but there's a large amount of temperature being held around this ring, which is causing the shrinkage to be very high in this region, which can adversely affect the shape of that circular feature. All right, so what they did is they looked to GAIM, and they took a couple of injection points. So their first thought was to put the injection point here, and the gas would penetrate up into the top region here. But unfortunately, by running the simulation, they were able to figure out that there was actually, the gas was penetrating downwards because that was closer to the end of fill, and that was closer to actually where the hotter material was located. And actually, they did simulate the gas blow-through, or the blowout in this case. But when they moved the gas injection point, you can actually see that they were able to push that air into the more critical region and around this feature. By doing so, they've removed this whole core here, so you can see that there is a high amount of temperature in conventional injection molding, CIM, and with the GAIM, they were able to essentially remove that high temperature region, and also in that sigmark region up here, you can see that the temperature is also greatly reduced. And that's by keeping the process exactly the same. So rather than having to increase their packing pressure from 15 seconds to 35 seconds, they can just apply this gas-assisted injection molding and actually probably reduce their cycle time in the end, because the gas actually replaces the need for that packing stage. All right, so in conclusion, so the warpage was able to be reduced on this part significantly. More importantly, the circularity of that feature was able to be maintained, and the sink mark region was able to be avoided because of the ability of gas to penetrate into that region. So that's just a couple of examples of how Moldex 3D can help to apply this gas-assisted injection molding to see what is actually going to happen on your plastic part by applying this process.